Hey, hello everybody. This is going to be week 8, lecture 3, and this is going to talk about conservation of energy. So there, you guys, we're going to talk a lot about different stuff that is going to look super complicated, but some of it we're going to ignore, and a lot of the other stuff is just going to kind of drop out when we talk about specific types of problems. Okay, so we all know that there is a conservation of energy. Okay, now you guys all know that when you have conservation of energy, you're talking about we can neither create nor destroy energy, Now there is a slight example here when we talk about nuclear. We talk about nuclear energy, where we're changing mass into energy. Again, we're going to ignore that. If we talk about in the totality of things, then mass and energy is conserved. So what we really have here is that our change of energy, we're going to call a system. And thus far, when we've talked about a system, I don't think I've really specifically said any of that. It's really an isolated system. So when we've talked about blocks that are sliding down ramps or being attached to springs, things like that, we're kind of keeping all of that stuff as an isolated system. Nothing is going in or going out. But if we do talk about everything that's going in and out, okay, then that is going to be equal to the sum of all of the transfers, okay, of energy. Okay. Now, if we think about that, that is going to be lots of types of energy. I'm going to elaborate on them. For example, electrical energy, but we'll get to that. But what kind of energy is there? Okay, so if we have a system, we're going to have kinetic energy, and we're going to have potential energy. You guys, and we have talked about that, and these two together is that's mechanical. You guys, that's mechanical energy. And then we also have internal energy. Okay, internal energy, and that is the energy. Primarily, that's going to be the energy due to the molecules vibrating around and in the location of the atoms in a chemical bond, which is kind of like potential energy. So if we think of all of the atoms in a molecule that are attracted and repulsed by all of the atoms around them, we end up with this vibrating mass, right? So they're going to vibrate around. So when they're vibrating, that is going to give them temperature. They're going to have a certain temperature. But in addition to that temperature of those molecules vibrating, we also have those molecules moving in and out of their potential energy. So remember that the thing that's going to attract one atom to another is going to be the electrons of one and the protons of the other, vice versa. So that's going to be an attraction. Okay, so we can think of a spring that's pulling them together. But at the same time, we're going to have the electrons of one atom and the electrons of another atom. They're going to repel each other. And the protons of one is going to repulse the protons of the other. So we end up in this equilibrium between two atoms. And that strength of that attraction and that distance is the bond energy and the bond length. Now, obviously, you've heard these things in chemistry, and we're not going to go into them. But you know that there is energy that is going to be inherent in an object. Although we are going to kind of ignore that from a physics point of view, I want you to know that that, in fact, is energy. And I am not ignoring it because it doesn't exist, is because we don't want to make it super complicated. Okay, now, if we think about all of the changes in kinetic energy and all the changes to the potential energy and all of the changes in the internal energy, that is going to that is going to be equal to zero, because that is conservation of energy. But these are really the three things. These are really the three things that we're going to have as far as all the types of energy. Now, this right here, okay, we could change any of these by adding work to it, right? And we could also get a flow of energy, which we know as heat. We know that as heat. And then we could end up with a bunch of other things, okay? We could we could transfer due to mechanical waves, okay? Mechanical waves, okay? So there could be things that are going to be vibrating, okay? And we could, and we're going to kind of come down here, and we could have that heat transfer for mass transport. So we could add mass. We could add mass to something. Like, for example, you pull up to your gas station and you add a bunch of gas to your car. Okay, you are transferring mass into there, and you're adding energy. Just think about all the heat of that. Even if your gasoline is cold, you're adding mass to it. So that's part of that energy. By the way, this mechanical waves, that could be something like sound, or even something like earthquake waves. That would be the mechanical waves. Okay. So we could also have the transfer due to electrical transmission. We can add energy through electrical power. Okay, so that right there could be added, and we could also add that for electromagnetic radiation. Okay, so this is electricity, and this is really light. Okay, part of the electromagnetic spectrum. That could be microwaves. It could be radio waves. It could be ultraviolet. Okay, so all of these things, when we add all of these things, that's going to equal to the transfer of energy in and out of a system. Okay, so for example, if you had a system right there that went through an exothermic reaction, for example, getting back to chemistry, the energy, that Q, is going to flow out of that system. And so this internal energy, is going to go down because energy is leaving. And that could be leaving from this heat point of view. It could be burning, right? It could be leaving due to light. Okay. So this right here is a system, so we could gain or lose. So we could have something on the outside. For example, you are sitting next to a bonfire, okay? And inside the bonfire, that's going through an exothermic reaction, and you're seeing the light and you're feeling the warmth, okay? You are gaining energy at the same rate, or you're gaining energy from the bonfire, and the bonfire is losing energy. Now, the amount that the bonfire is losing is not equal to the amount that you're gaining, because that bonfire light and heat is going other directions, not just into you. But you get that idea, okay? All right, so this right here is talking about all of this energy transfer. So now what we are going to concentrate on, just this part and a little bit of this part. just this part and a little bit of the other part. Okay, so we're going to say the change in kinetic energy plus the change in potential energy is equal to 0. Now, you guys, as soon as we do that, we're just ignoring all that stuff that I just talked about, right? So we're ignoring that internal energy, and we're ignoring that electrical transmission and the mass movement, et cetera. All that stuff we're just ignoring to make it simple. This here is mechanics. Now, I want to point out here, kind of from a work energy theorem. Okay, now remember that kinetic energy is equal to final minus initial, and that would be potential energy final minus potential energy initial, and that's equal to 0. Now what I'm going to do here is I'm going to take these two and move them over here. So I'm going to say kinetic energy final minus kinetic energy initial is equal to negative potential energy final minus a negative initial energy here. So what I could do is just put this in parentheses and make that negative, and then we have this. So remember, this right here is our change in kinetic, and this would equal to our change in potential. Negative change in potential energy is equal to the change in kinetic energy. And as we already said from our work energy theorem, that work is equal to the change in kinetic energy, which is also equal to the negative change in potential energy. Now, just a simple example of that would be something like this meter stick acting as a pendulum. It's going to go back and forth like this. So if we stop it out here at its highest point, it's going to have gravitational potential energy. At that highest point, it's changing direction, so the velocity is 0. All of that energy right at this point at its maximum is going to be potential energy due to gravity. As it comes back down, when it reaches here, its mass times gravity, its potential energy, is the lowest it can be for this system, okay? And that means it's going to be the greatest. It's going to be the greatest velocity. And if we just think this going back and forth, it's going from 0 kinetic energy to all kinetic energy to back to 0 kinetic energy. And the reverse is going to be correct. Right here, it's maximum potential energy, minimum potential energy, maximum potential energy. So in this system, the change in kinetic is equal to the negative change in potential energy. All right, now this is where I'm going to write a big long equation, and I'm going to give you specifics here, and then I'm going to pull aside what we talk about friction. Okay, but we're going to have our energy initial is going to equal to our energy final. Energy initial is going to equal to energy final. Well, we're going to have kinetic energy, and we're going to have potential energy, and we're also going to have the work done by friction. And we could also have the work done by an applied force. So we can put energy in. It might already have kinetic energy. It might already have potential energy. But as this work, force times distance, is going to come into play, this work is going to be force times distance. It's going to be negative. Okay? All right. Now, on the other side, we're going to have this can turn into kinetic energy plus potential energy. And we're going to make this side initial and this side final. Now, generally we're going to put in work, and the energy due to friction, all that's going to happen during the process, right? So in the beginning, we're going to have a force, and in that process, we're going to go a distance. That's going to be work. We're going to have a force of friction, and it's going to go that distance. So that's part of the process. But what I'm going to do is I'm going to change this negative work done by friction and bring it to this side so that everything is positive, okay? So work applied plus the initial kinetic energy plus the initial potential energy is equal to the kinetic energy final plus the potential energy final plus the work done by friction. Now, one way to think about this conservation of energy is think of it like an accountant, all right? Think of it as money. So think of it as value. So what we're really doing is we're just thinking about accounting for all of the energy. So if we have, for example, kinetic energy, that could be like the value of our car, and the potential energy could be the value of our house and our possessions, that sort of thing. What we can do is when we add work, we're earning money and we're putting it into the system. So we could increase the value of our car. We could increase the value of our home and add more stuff to it. But we could also just, the amount of friction would be kind of like the value, perhaps like the food that we eat. So again, we are accounting for everything. And because the total energy is conserved, then we can account for it all here. And again, we are ignoring that we're ignoring the internal energy. But I just want to talk about the work done by friction, okay? That's the force of friction times distance, okay? Now, unlike potential energy, if I have this pen and I increase my height, I've added potential energy. But that doesn't go away. Because all I have to do is let it go and it's going to come back down, okay? If something is moving, then it's going to have kinetic energy. So like we said here, this pendulum, as an example, I increase the potential energy and then it decreases. But at the same time, my kinetic energy is high when my potential energy is less, but they can interchange. When it comes to friction, we don't store any energy when it comes to friction. That is going to get wasted, right? It doesn't help us. So it's kind of like food, right? We buy food and we eat food and then we don't get to keep it. We're using that energy to accomplish our everyday activities. Now, if we think of friction as just moving our hands together, when you do that, and you do that naturally if you are cold, if your hands are cold, when you move that together, okay? So the amount of work done by friction is going to get wasted as heat. That heat is going to change the internal energy, okay? So when we have the work done by friction, okay, we really have a change in heat, the Q. You probably remember Q is equal to MCAT. Q is equal to MC delta T. But this right here would change the kinetic or change the internal energy. So it's not that we haven't forgotten it, okay? But in this way, this is really the only thing that we're really talking about when it comes to something other than just kinetic and potential. But that's kind of a easy thing to account for. It's an easy thing to account for because it's just a force times distance, and this is it. Force of friction is going to be a constant force, so we just need to know the distance. Okay, now, this kinetic energy and potential is known as a conservative, okay, we know that this is a force. Okay, so this is a conservative forces. Okay, so kinetic energy, potential are conservative forces. It doesn't matter. It doesn't matter which direction that you go. If I take this and I move it up here, this difference in height is going to be the same height as if I move it straight up. Okay, that is called a state function. You might remember that from chemistry or AP chemistry. Does not matter what path that you go. Okay, you might remember from Hess's law. But when it comes to friction, friction is a non-conservative force. Okay, it absolutely depends on the path there. Because if I'm rubbing my hand through let's say a tabletop, the whole time it's wasting energy because it's running into more things if I go a longer path. Okay, so friction is a non-conservative force, but we can still account for it. We can still account for it when we talk about, for example, Q and this change in internal energy. So it's still applicable. It's still applicable when we talk about conservation of energy. But we're going to ignore electromagnetic radiation. We're going to ignore electrical energy. We're going to ignore vibrational energy. So again, this is really the only thing that we're going to have. All right. So now I'm going to change this into the actual equations. Okay. And I'm going to say that our actual equation for work is going to be force times distance. And I'm going to say cosine theta. Okay. And I'm going to say 1/2 mv initial squared plus mgh. You guys, that is gravitational potential energy. But we also have 1/2 kx initial squared. Okay, and this is the potential energy due to a spring. Okay, and we have just talked about all the forces that are going to be on the beginning side. And on the final side, we're going to have 1/2 mv final squared plus mgh final plus 1/2 kx final. And then finally, we're going to have the work done by friction, which is the force of friction times distance. The force of friction times distance. Now remember, when we put it on the final side, it turns to positive. So we're going to have this big, long equation right there. And that is really good. But if I ask you a question, for example, I'm going to have a 2 kilogram object and I'm going to apply 10 newtons of force over a distance of 3 meters over a frictionless coefficient of friction is equal to 0. Okay, then how fast is that object going? Okay, we have an initial velocity of 0. Now, do I have an applied force? Yes, I do, which is going to be 10 times a distance of 3. The angle between the force and the displacement is going to be 0, so the cosine is 0 is equal to 1. So this is the only thing that I have, because my kinetic energy, my initial velocity is 0, so this goes away. Even though I'm going to have a certain height, I can just say that this h is equal to 0, and over here the h is equal to 0. So this part goes away. We're not dealing with any spring, so this goes away. Now on this side, we could have a v final squared, which is what we are going to have. the height stayed the same. So these two things cancel each other out. There is no spring, so this goes out. We have no friction. So this goes away. So now we're just going to end up with 30 is equal to 1/2 times 2 times V final squared. V final is going to equal to the square root of 30, which is going to be about, maybe 5.7. Let's go. The square root of 30. 5.5. So 5.5 meters per second. Okay. So this right here accounts for a conservation of energy in the terms that we have been dealing with, which is mechanical energy, kinetic energy plus potential energy. And the only thing we're really doing with a non-conservative force, which would change the internal energy, would be the work done by friction. So think about how much of each thing that we have. Okay, so here, if the only thing we're adding to one side is the energy by work, so think about if you added $30, you add $30 to this side, everything else is zero, and on the other side, what would that do to your car, for example? So that $30 could make your car go for a while, as far as how much mileage you could get out of your car. So you're changing that $30, for example, into miles in your car. That's the same idea. So think of it as an accounting sort of thing, and that will help you understand conservation of energy as it applies specifically to mechanics and the physics of things moving from one place to another. All right, I hope that helped, and you'll see some questions along these lines. Take care.